indices.
Yeah. Parametric indexes. So in that parametric indexes, I will share the screen. 1 second. Important topics only we will discuss. Okay, we are not going to go through all the things we have done earlier. So only the important topics we will do a brief revision. Okay, and we can complete the revision today. So let me share the screen. Okay, so for your end term, the syllabus will be after midterm. Okay, for your end term, the syllabus will be after your midterm. So we will do the revision after midterm portions. Okay. So in term frequency and weighting, here one important thing is inverse document frequency. How to find inverse document frequency. That is important, and you need to know what is document frequency and term frequency, and also how to find the inverse document frequency. So in document frequency, you have to count the number of documents. Whereas in term frequency, you have to count the number of occurrences of the term. And finding the inverse document frequency, we need this formula log n by DFT, where n is the total number of documents in the collection. So after that we have TF IDF weighting, and in this TF IDF we need to multiply the IDF value along with the term frequency for the term in the document. So that means our document frequency. Okay. The example is given here. If we consider n equal to this number, if we consider n equal to this number is actually coming from our database from Reuters collection. Okay, Reuters collection, it has 806,791 documents. Okay, and from that the document frequencies of the some random terms are given here for car, which is there in the Reuters collection database. The document frequency is 18,165, and for auto it is given, for insurance also given, for best also it is given. Then using the formula given here for IDFT, we are going to find the term ITTF IDF rating. So initially, in order to find the TF IDF rating, we have to find your IDF values for the corresponding terms. For car, the IDF value; for auto, the IDF value; for insurance, the IDF value; for best, the IDF value. An example is given here for finding IDF value for car. It is nothing but log n by your document frequency. Our n is given here 806,791, and our document frequency is given from this table 18165. So after calculating this, we got an IDF value of 1.65. So this 1.65, if you multiply along with your document frequency 18,165, then we will be getting TF IDF value. Okay. Then for finding the score, this is nothing but for all the terms, you have to find the TF IDF in all the respective documents, and finally you do a summation. So for particular document 1, in the initial table given here is for the whole collection. The DFT given here is for the whole collection, but here D1, D2, D3, it is given for respective documents. Here it is given for some respective documents. That's why for each document we have to find the ITF IDF for each document. For car in document 1, for car in document 2, for car in document 3. Like this. You have to find each TF IDF for the respective documents given in the collection. And for this particular table, we have only three documents: document 1, document 2, and document 3. That's why when we find the score, we are going to calculate only for these documents, the TF IDF, then do a summation of all this. So it is what given here. I have just done the summation of the TF IDF values. Then respectively, you can do for auto, you can do for insurance, you can do for best. And it is also given in your exercise textbook, which I have sent you some e-book. There also it is given. So like that, you have to find the score. Then vector space model for scoring purpose. So for scoring purpose, here we need to find the similarity between the documents. So how to find the cosine similarity between the documents? Formula is given here, similarity of D1 and D2. Then vector representations of document 1, dot product vector representation of document 2 divided by Euclidean length or length normalization. Normally this is called length normalization, and which is calculated using the formula Euclidean distance formula. Euclidean distance formula is given down here. The Euclidean length of D is defined to be square root over summation I goes 1 to m vector square of the document. Vector representation square of the document. So the whole formula is given here. This calculation is important. Okay. Sometimes this may be coming for your subjective question. So you can just go through this example. Okay. The example, I'll show you the example. And this one similarity. Okay. So I'll show you the example. This is just we are refreshing our chapters. Okay. So let me share you the example for vector space retrieval method. So this one. So we have three documents. Sometimes we may have 5 documents. Sometimes we may have 4 documents. So it depends on the question. But for easier purpose, easier calculation, normally we used to give 3 documents, because when you have more number of documents, this idea calculation will be lengthy. Okay, because when you have more number of documents, you have more number of terms. So when you have more number of terms, for each terms to find the idea values, that will be somewhat lengthy for you. Okay, for this online exam. That's why I may give you some 3 documents at the maximum. Then calculations are same. Okay, from this table, from this documents given here, you need to find the idea values, idea calculations. So inverse document frequency. So in this collection, we have 3 documents. So our n will be 3. Our capital N will be 3. And after that, we need to find the IDF values. So to find the IDF values, we have to use the formula. And for finding the ideal values for this particular example, that is our vector space retrieval model. Vector space retrieval model, we need to use the log base 2. Okay. For others, you have to use log base 10, and only for this finding similarity, we have to use log base 2. So don't get confused while calculating the ideal values. The normal ideal value which we have just seen, that is you have to find using log base 10. That is your our normal way of calculation. Okay. Then for finding the similarity, you have to use log base 2. So with log base 2, I have calculated all the ideal values for all the terms here. So you have already known the idea of document frequency and term frequency. That applies here also. Okay. Normally we count for document frequency for finding the IDF values. Then next one, uh, this is the TF scores. We have to find the TF scores. So if the term is present, it is represented by 1. If the term is not present, it is represented by 0. That table is here, similar table. And after that, what do we have here? For the query also, we have to find the TF-IDF values. For the query also, we need to compute TF-IDF values. And here, when calculating the TF-IDF values for the query, you have to see this point. You divide the frequency by the maximum frequency and multiply with the IDF values. Okay. So IDF values already calculated for the query also, because query is normally given from this terms given here. So we have already calculated the query is, where is the query? New times or something. The query. Here. So our query is new and times. New times. Okay. Our query is new times. So here, even for the following query, new times, we have calculated the TF-IDF. But when computing the TF-IDF, we need to divide for it is only for the query terms. Okay, it is only for the query terms. We divide the frequency by the maximum frequency and multiply with the IDF values. So as you have already uh, calculated this, our maximum frequency for the query for new is 2, and in the collection for new it is 2. Okay, in the collection the frequency is 2, and also for the query it is 2. So 2 divided by 2, so we get this value. And similarly for times, it is only 1. Then the maximum frequency in the collection is 2. So 1 by 2 it comes here. Then you do the multiplication. Then you will get the TF-IDF score for the query also. Then after that, we need to find the length normalization. And length normalization using the Euclidean distance. So this is using the Euclidean distance. This is also using Euclidean distance. Then after getting this value, we have to find for the query also. We have to find for the query also, like the same how we find for document 1, document 2, and document 3. And finally, the final step is to find the cosine similarity. For cosine similarity, you can find between the documents, and also you can find between the document and the query. So D1 and the query, D2 and the query, D3 and the query. So normally it is just to find the similarity between the document and the query, and so that we can check out, or so that we can find out which query has the maximum cosine similar, which document has the maximum cosine similarity with the given query. So based on this cosine similarity calculation, we got these three values here. So their similarity, the order will be D1, D2, D3, because the higher the value, it has a higher similarity with the query. Okay, so 0.776 is the higher uh, value, so it has higher similarity with the given query. So next, the order will be D1, D2, and D3, like this. But there are cases sometimes between the documents also we can find the cosine similarity between the documents. So you can say here cosine similarity D1 and D2, cosine similarity D2 and D3, cosine similarity D1 and D3, like this. In that way also we can find the similarity values between the documents. But normally we find the similarity between documents in the query so that we can check or so that we can know which document has the maximum similarity or has the highest similarity with the given query. Then next one, that is about vector space retrieval model. So there are two vector space model here. The first vector space model is about the retrieval, vector space retrieval model, and the second one is based on classification, how to do classification based on vector space classification. This is vector space retrieval model. The next one, it is about your language modeling. It's about language modeling, probabilistic model. So before language modeling, you need to know about probabilistic model. Probabilistic model based on probability. It is nothing but all your calculations will be based on probability. So here also we will see only the important things. We are not going to go through all the terminologies here. But these things you have to study, okay? Because sometimes in 1 mark, in multiple choice, I may ask you what is 1 by 0 loss case, okay? Or I may ask you what is Bayes optimal decision rule. Then you have to write this one, okay? D is relevant even only if probability of R equal to 1 for the document in the query is greater than probability of R equal to 0 for the document in the query. Like this, you have to answer. And even from this also, what is odds of an event, I can ask, and asking the formula for this in multiple choice. Okay. Next, occupy model. So occupy model, we have four models here. The first one is basic term weight. Basic term weight, you have to use this formula for calculating the probability value. So here we are going to compute the term probabilities. Okay. And we also use the constant value 0.5 here when we assume when there are no retrieved documents. So our probability value will be a constant value, which is normally we assume to be 0.5 when there are no retrieved documents. So using this formula log n minus n, this small n, we have seen number of occurrences of the term in the document. For the term in the document, which will be okay, taken from the, say, let us see the example here. For this also n equal to 6, I have 6 documents, and calculation is here. Okay, calculation is here. Okay, let us take here. First one, probability of call. So probability of call, we are going to find n minus n. So 6 is total number of documents. How this n comes? So N for call is 2. N for call is 2. So which means call is one time present here, call is another time present in document 4. So I have one call in document 1 and the other call in document 2. So our frequency and document frequency for call will be 2. So that is why we put 2 here. Then substitute all the values, we get 0.26, which is given here. First for call 0.26. Similarly, you have to calculate for all the other terms in the document. So this is basic term width. Now improve ranking. In improve ranking, we have changed the formula. Our formula is now this one. We have small r, we have capital R, we have small n, we have capital N. But our capital N and small n, we already know what are they. So the additional thing here is small r and capital R. Capital R is number of relevant documents. Number of relevant documents. Whereas small r is the frequency for the particular term which is present in the relevant document. Only we have to check in the relevant document. If a particular term is present in the relevant document, that we have to check. This is also a kind of document frequency, but this frequency will be checked only in the relevant document, not in all the documents. So that is the only difference. So here also it is given document 2, which is highlighted by yellow color. It is relevant document. So our R will be 1 in our calculation. In case if I say document 2 and document 4 are relevant, then our capital R will be 2. And when we calculate using the formula for a particular term, suppose if it is say P or hot, for example, hot. I have to check for small r if I calculate for hot, if it is present in the relevant document. If it is not present in the relevant document, then 0. But say suppose r equal to 1 for document 2 is 11, right? So for hot, if I have to calculate, it is not present in relevant document. So it will be 0. But in case, if I say there are two documents which is relevant and the documents are document 2 and 4, then if I calculate for hot, it is not there in relevant document D2, but it is there in relevant document D4. So our small r will be 1 if you calculate for hot. Okay. So like that, all the values, respective values are given here. That is the second occupy model. Then our third occupy model is, one second, our third occupy model. Where is it? That is BM1 and BM25. Two more occupy models, BM1 and BM25. So BM1, it is almost same. This is basic term, this is improved ranking, and I will show you. These are all, this is BM25. One second, one more, it will be there for BM1. Where is it? Where is it? Occupy. Yeah. So instead, I will share another screen. Occupy. Okay. So you can see here, BM0, BM basic weight will be there, and after that our improved ranking will be our BM0 model. Then BM1 is nothing but this BM0, the whole thing, it is represented by W1 or WT. So multiplied with this term frequency for the term in the query, and K3 is some scaling parameters and term frequency for the term in the query. Okay. So this multiplied by this value, we call this as BM1, and BM25 we have some more parameters added to it. We need to calculate capital K, capital BK1, the B, then K3, then K2. So all this value K1 is 1.2. Okay, and the normally K2 will be 0 and K3 will have higher value, which is normally taken for a efficient calculation 7. B value also is ranging from 0.6 to 0.75. So all these values parameters, see, it is known as tuning parameters. Then calculations, so you can see here the explanation. K1, it governs the importance of within the document frequency. So K1 scaling factor is used for scaling the document frequency, and K2, this is used for scaling the document frequency in larger documents, and K3, it is used for scaling the query frequency. B, it is used for scaling the document frequency and document length. So all these are scaling parameters, and for K separate we have another calculation. K equal to K1 1 minus B plus B into DL divided by average DL. DL is document length. So document length calculation, I think, yeah, it is here. So here in this table, we are not writing the binary matrix table. So this you have to keep in your mind and you don't get confused with the first calculation. In our first calculation, we just use the binary incidence matrix, whereas in this BM25 model, we use the frequency table. Frequency table, why do we use? We need to find out the document length. So easily, if I write the document frequency, we can calculate the document length. So call, it is there in D1 one time, hot, it is there in D1 one time, P, it is there in D1 two times, for it is there in D1 two times. Okay, so all those terms you have to count. For example, this is the document. So call P porridge hot, P porridge. So call is there one time, hot is there one time, P is there two times, porridge is there two times. But when you count the document length, you have to count all the terms irrespective of it is repeated or not repeated. So 1, 2, 3, 4, 5, 6. So the document length of D1 is 6. It is what it is written here. But instead, if you draw the frequency table, directly you can add the numbers here. 1, 2, 3, 4, 5, 6, like this. Okay. Similarly, this has been constructed for all the remaining terms. Then calculation here, it will be in two ways, and that will be mentioned in your question paper, because while calculating W1, you can calculate W1 in two ways. How? First one using the basic term width and second one using the improved ranking. So there can be two weights. So that will be mentioned in your question paper, that the WT calculation based on which uh, model. So using here it is said using basic term width, that means the first formula without small r and capital R. That you have to use that formula for finding WT. Other calculation remains the same, because K1, K2 they are already given parameters, and finding the DL you have to find from this frequency table, so that is different, right? So the important thing is calculating the width W1. W1 is calculated here using the basic term width. Similarly, when you calculate W1 using the final term width, which is our improved ranking width, where we have small r and capital R, that the values will be different. So if you use this formula, then multiply with the term frequency for the term in the query and all those k parameters, you will have different answers. Okay. So with finding, we have two methods. One is using the basic term width and the second one is using the final term width. This you have to keep in your mind. Okay. Then where is it? So all those calculations, stability. This is first one is for using the basic term width. Second one is so these are all using the basic term width. And second one here, this is using improved ranking, which is our final term width. So that also it is given here. And for this K calculation, as I told you, here 4.8 is, it will be wrong because when I calculate here 4.8, this will be wrong because when I calculate, I have directly multiplied this 1.2 factor for K1 with this value alone. But in the formula, you have to first finish everything, all the computations inside the brackets, and you have to multiply along with the K1 factor. But what I have done is, I have multiplied K1 factor only with the first term. So this 4.8 will be wrong. That's why, one second, that's why I have already asked you to change the calculation. In case if this question is asked for the subjective type in your n term, you don't get this one, no? I'll show you. I'll stop this presentation and yeah, here you can see k equal to 1.2, all those values. The k calculation you can see for your reference. Okay. 1.2 is here. I have done the calculation 1 minus 0.75 plus all this calculation inside. All this calculation inside multiplied by 1.2 at last. Okay. So I got 3.9. So my 4.8 was a wrong calculation. So you have to change that one. Okay. Then upper model is finished. And language modeling. So we will do up to unit 7. That means our chapter 7 revision, and I will have one more class for unit 8 and unit 9 revision. Okay. So for today up to unit 7 I will do. Unit 7 includes your language modeling also. I'll just finish the language modeling. So for language modeling also, as I told you, it's like, one second, let me share this. So for language modeling, normally unigram language modeling, bigram language modeling, then query likelihood retrieval model, those things are important. Okay. So directly, so this basics you have already, you can just go through by yourself because probability distribution is like normal concept for probability distribution. How to find the probability of red from this collection, how to find the probability of blue from this collection. So just you need to count the particular blue balls, then divided by total number of balls in the collection, like that. Okay. And in order to get a non-zero probability, what uh, we need to do at one smoothing. In order to get a non-zero probability, we need to do a at one smoothing. So for at one smoothing also, It is given. Where is it? Where is it? At one smoothing. I think it's not here. It's in the next slide. Anyways, you can see this is regarding the unigram. I have some certain collection of terms in this. So each term in the collection, we are finding the probability, and when we find the score of it, we just need to multiply. Okay, when we find the score, we just need to multiply. Suppose University of North Carolina, when we find each probability of university, probability of off, probability of North, probability of Carolina, then you multiply all these probabilities. So we get a score for this given query. That is unigram. And bigram, this probability of next word, it depends on the last word occurrence. That is event occurrence of the last word. So here you like green cream. Here also you have to find probability of U, probability of like condition on U, because U is the initial probability. Like is here the current word which we have to find the probability, which depends on the last word. Our last word is U. Okay. The probability of U, we are writing here. Then we have to find probability of like condition on probability of U. Probability of green condition on probability of light, like this. Okay. That is about diagram. What I want to tell you is at one smoothing. At one smoothing is important. Document language modeling, it is also same, but the condition is we need to consider a whole set of documents. That's like bigger paragraphs, bigger collection that will be considered in document language modeling. So for that also calculations we have already done. You can just check this calculation and you can understand easily. So all these terms here, all the document frequencies here, and this is the total number of documents in the collection and finding the probability. Okay. Query likelihood retrieval model. Here in query likelihood retrieval model, we have to score each document. Each document. So for D1, for D2, for D3 separately. For each document. When we find score in the previous example also, when we find the score, we have calculated for each document. Just give me 1 second. Hello? How? Uh, হয় হয় হা হয় হয় yeah yeah হয় হয় ꯌꯥꯏꯌꯦ ꯀꯥꯏꯗꯤꯌꯦ ꯃꯥꯒꯤꯁꯨ ꯉꯁꯤꯗꯤ ꯂꯣꯏꯁꯜꯂꯁꯦ ꯌꯥꯔꯒꯗꯤ ꯑꯩꯅ ꯃꯇꯝ ꯐꯪꯉꯒꯗꯤ ꯅꯠꯇ꯭ꯔꯒ ꯃꯉꯥ ꯁ꯭ꯋꯥꯏꯗ ꯑꯗꯨꯗꯤ ꯍꯣꯏ ꯉꯁꯤ ꯑꯗꯣ ꯍꯌꯦꯡꯗꯤ ꯑꯃꯨꯛ ꯁꯨꯇꯤ ꯂꯩꯁꯟꯈꯤꯕꯅꯤꯅꯅꯦ ꯍꯟꯗꯛꯀꯤ ꯋꯤꯛꯁꯤꯗ ꯌꯥꯔꯦ ꯅꯣꯏ ꯃꯉꯥ ꯌꯥꯔꯦ ꯃꯥꯅꯦ ꯃꯥꯅꯦ ꯌꯥꯔꯦ ꯑꯗꯨꯒ ꯑꯩ ꯍꯧꯖꯤꯛ ꯀ꯭ꯂꯥꯁ ꯂꯧꯔꯤꯕꯀꯣ ꯂꯣꯏꯗꯣꯔꯦꯕ ꯑꯗꯨꯒ ꯑꯩ ꯊꯣꯛꯂꯛꯑꯅꯦꯕ ꯀꯣꯂꯦꯖꯇ ꯑꯗꯨꯒ ꯑꯩꯈꯣꯏ ꯍꯥꯏꯐꯦꯠ ꯑꯃꯨꯛ ꯈꯟꯅꯔꯒ ꯃꯤꯗꯣ ꯈꯥꯏꯗꯣꯛꯅꯔꯒ ꯆꯠꯅꯕ꯭ꯔꯥ ꯀꯩꯅꯣꯝ ꯇꯧꯅꯔꯁꯤꯅꯦ ꯎꯝ ꯍꯣꯏ ꯌꯥꯏꯌꯦ ꯍꯣꯏ ꯌꯥꯏꯌꯦ ꯑꯩ ꯋꯥꯟꯅ ꯄꯨꯡ ꯑꯃ ꯁ꯭ꯋꯥꯏꯗꯗꯤ ꯊꯣꯛꯂꯛꯑꯅꯦꯕꯀꯣ ꯑꯗꯨꯒ ꯌꯧꯔꯛꯑꯒ ꯑꯩ ꯄꯥꯎ ꯍꯥꯏꯔꯛꯑꯒꯦ Ano ba? Oo, oo, Mara. Mara khara ikaꯏꯒꯤꯕꯗꯨꯗ ꯇꯧꯔꯤ ꯑꯣꯏꯔꯝꯒꯅꯤ. ꯎꯝ. ꯑꯗꯨꯅꯦ ꯑꯗꯨꯅꯦ ꯑꯗꯨꯗꯅꯦ ꯃꯥꯅ ꯍꯥꯏꯔꯛꯏꯉꯩ ꯇꯥꯏꯃꯤꯡꯗꯨꯗꯅꯦ ꯏꯆꯝ ꯆꯝꯕꯅꯦ ꯑꯗꯨꯝ ꯀꯩꯅꯣ ꯍꯥꯏꯗꯣꯛꯑꯝꯒꯗꯧꯅꯦꯕ. Okay, so query likelihood model. Here we need to find the score for each document. Say suppose for D1 separately. So Rocky versus Apollo Creek. For Rocky in D1, for versus in D1, for Apollo in D1, for Creek in D1, and finally you have to multiply all the probabilities like that. Okay. Suppose if you want to find for probability for sorry score for this particular query in D2, then probability of query in probability of Rocky in D2, probability of versus in D2, probability of Apollo in D2, probability of Crete in D2. You have to find all these things. Then what you have to do, you have to multiply all the probabilities. So that will give you the score value. How? Ay, klase yung yellow dore. Wala laag eh. Mm-mm. Hoy. Hoy. Mm-mm. Tama. So that is about query likelihood retrieval model. Okay. So one example is given finding for D5. For D5, you have to find all the probabilities, then you will multiply it. That gives you score for query likelihood retrieval model. And here you don't confuse with this. This is product. Okay. And score which we have seen for the TF-IDF score, that is summation. In that case, you have to add all the TF-IDF values, then you will get the score. Okay. Just what we have seen in first example, finding TF-IDF score or TF IDF rating, you need to find the score. If I say you have to find the TF IDF score, in that case, what you have to do is for the respective terms in the query, you have to find the TF IDF rating. Then you do a summation of all the TF IDF. Okay, you have to do the summation of all the TF IDF. But for this score for the probability, query likelihood retrieval model, here all the probabilities you need to do a product. That means multiplication of all the probabilities. Okay, this you have to keep in your mind because sometimes When you find the score, it is summation. Sometimes when you find the score, it is a product, a multiplication. So you may get confused. So don't get confused here. In finding the score for query likelihood retrieval model, which comes under your probabilistic model, we need to do a multiplication product. Okay, and for the uh, TF-IDF scoring, in that you have to do a summation. Okay, so that's the difference. And this is about at one. Suppose in this collection, this is what I want to explain this. So suppose in this collection, you don't have any yellow color balls and green color balls. So, but if I want to take out this samples from a bigger collection, suppose this bag, if you take out, consider this as a bag. Okay, this as a bag, you consider this. And if you take out this bag from another bigger bag, from another bigger bag, so which may have chances to have some other different color balls. It may have, it can be yellow color balls, it can be green color balls, it can be black color balls. But for this bag, which is known to us here, it doesn't have any it doesn't have any yellow color balls, it doesn't have any green color balls. Okay, but our condition is what? Our condition is, if I take out this bag which contains all these balls from another bigger bag, then we may have chances to contain your other different color balls. It can be yellow, it can be green, it can be purple, it can be black, it can have other color different balls also. For this example, if I think that there may be yellow color and green color balls from this bag, then in order to get a non-zero probability, in order to get a non-zero probability, we need to perform at one smoothing. We need to perform at one smoothing. So that means in all the colors you need to add 1, 1, 1. So red, how many balls are there? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So 10 plus 1. How many orange balls are there? 1, 2, 3, 4, 5. 5 plus 1. How many blue balls are there? 1, 2, 3, 4, 5. 5 plus 1. Then one yellow ball, then one green ball. We consider that way. Here. Then our calculation becomes like this. So after adding 1, 1, 1, our probability value will be changed. So initial probability for that was 0.5. After adding at 1 smoothing, it is 11 by 25. So you may have some lesser value than the previous one. So that is at 1 smoothing. Also, this is called discounting. This method at 1 smoothing, it is also called as discounting. So initially we have like this. After at 1, we have the bottom, this probability values. So this is important. This condition is applied in our classification also. All these classification, Rocky's classification, and all those classification also we apply this condition here. So you need to know this concept of at one smoothing. Then linear interpolation, collinear interpolation smoothing. This is also one of the approaches for smoothing. Linear interpolation, we use this formula. Probability for the term in the document, we have this formula given down here. And the first part, the first probability, it is for the document. It is for the particular document. And for the second probability, it is given to the term by the collection language model. That means for the entire collection. This is for the document, this is for the entire collection. Example also we have discussed in our last class, but we will see here. So this is for the particular document. We have two documents, D1 and D2, and when it contains about 50 term occurrences, so we have n equal to 50, and for document D2 it is 50. So apple it occurs two times if we consider in the document, not in the collection. In the document 2 by 50 and 3 by 50, which means three occurrences of iPad in the first document. And in the second document, two occurrences of iPad. So like this. So when we calculate the score, it is almost similar. Exactly the same probability value we got here, 0.0024, here also 0.0024. So this may be quite confusing. So score for Apple also it is 0.0024. Score for iPad also just it gets the same value. So this might be quite confusing. That's why we use linear interpolation, which has smoothing by itself, and this normal one is without smoothing. So with smoothing, we will be considering this formula given down here. This is for the first part is for the document calculation, second part is for the entire collection calculation. So you can check here if the entire collection has 200 occurrences for the term apple, and iPad has 100 occurrences in the whole entire collection. Calculation will be little different. So for the entire collection, we have calculated the probabilities for Apple and iPad. Then after that, you can see here the score we have to find. After finding each score in the document. So each score in the document we have calculated here. Then after that, we will do the entire calculation. So for the collection, entire collection, we will get these two probabilities values for Apple, for iPad, which we will be multiplied here. So for Apple in document, it is 0.04. For Apple in the entire collection, it is 0.002. Like this. Okay. For Apple, you find the scores in D1 and D2, and for iPad also you find the scores in D1 and D2, and for the entire collection. And after that, you just multiply the values, and we go see score for Apple, score for iPad, 0.0201 into 0.03005, and for here 0.0301 into 0.02005. So we get little slightly different here. 0.64005 here is 3505. So like this, it will be more precise. So the linear interpolation method is more effective than the query likelihood retrieval model without smoothing. So this is more efficient. We got accurate score than the initial method, like that. Okay. Okay. So for today's revision, let's wind up here. It's almost 12:45. So classification and clustering, we will do revision in our next class. So next week, it may be Wednesday, Thursday, or Friday. In any of these days, I will take one more class to finish the revision. Okay, because our syllabus is already completed, and you can just go through all the syllabus, all the topics which I have given, which we have discussed even today for your end term. So only I need to complete the all the classifications, Bayes classification, Rocio's classification, KNN classification, along with clustering. So classification and clustering we will do in next week revision. Okay. So let me take a quick roll call.
Ma'am, will you take Viva also in intern?
Viva, what?
Will you take Viva also in the intern?
Yeah, yeah. For Viva, there will be. Sorry, for income, there will be Viva.
Okay, ma'am. And syllabus of Viva is also after midterm, right?
Yes, yes. After midterm.
Okay, ma'am. Thanks.
Mm. Okay, roll number one.